The next technique to study is the Gaussian elimination technique. The key idea of the Gaussian elimination technique is to make the structure of these inclusions upper or lower triangular by multiplying by an invertible matrix. Let's derive the proximal method of multipliers with functional linearization using this Gaussian elimination technique. The primal problem that we'll consider is minimize f of x plus h of x, where the function f is assumed to be CCP, h is CCP, but furthermore h is differentiable. And this optimization problem is subject to the linear equality constraint ax equals b. This primal problem is generated by this Lagrangian, where we have f of x plus h of x, and then an inner product term between the dual variable u and the constraint ax minus b. The saddle subdifferential of the Lagrangian L has this form. So it has the subdifferential operator of f, the gradient operator of the differentiable function h, and this skew-symmetric linear system. We'll split the saddle subdifferential into this operator, which we'll refer to as the g operator, and then we'll split it with this operator, which we'll refer to as the h operator. Then we'll perform the fixed point iteration with regular forward-backward splitting. We will not be using the variable metric forward-backward splitting, we'll be just using the regular forward-backward splitting. The FPI with forward-backward splitting maps the iterates xk and uk to xk plus 1, uk plus 1. If we apply I minus alpha h to the iterates xk comma uk, we get this on the first component, so xk minus grad alpha grad h xk. And then remember that the h operator had the constant vector b in the second component, so the second component becomes uk minus alpha b. And on the left-hand side, we have xk plus 1, uk plus 1 defined implicitly through the operator I plus alpha g. So here, the identities on the diagonal of this matrix, that comes from this identity operator. And then the skew-symmetric component, that comes from alpha g, and also the subdifferential operator with respect to f, that also comes from alpha g. If we solve for xk plus 1 and uk plus 1, that gives us an algorithm describing this fixed point iteration. But this system of inclusions is not lower or upper triangular. So what do? Well, what we do is we construct this matrix. This matrix is invertible because it is an upper triangular matrix with all diagonals equal to 1. In particular, the determinant of this matrix is equal to 1. And so we left multiply by this matrix to this inclusion. So we multiply this matrix to this matrix, and we get this lower triangular system. We multiply this this operator with this matrix, but the first component is unchanged. The second component is 0, so it remains 0. And then we multiply this vector, left multiply this vector with this matrix, and when we do that, we get this thing. The inspiration for constructing this matrix so that we can eliminate this upper top right component to achieve a lower triangular structure is something that is utilized commonly in linear algebra in Gaussian elimination, and hence this technique is referred to as the Gaussian elimination technique. Now our system of inclusion has this lower triangular structure, and due to this lower triangular structure, we can now first solve for xk plus 1 and then solve for uk plus 1 as we did before. So when we write out the algorithm, we get this. To obtain the xk plus 1 update, we solve this minimization problem, and then to obtain the uk plus 1 update, we perform this matrix vector products. We refer to this method as the proximal method of multipliers with function linearization. Let me explain the name. Imagine if we don't have this h term, then this is just the proximal method of multipliers, because here we are minimizing the Lagrangian, so this function f, and then this inner product term, this is the Lagrangian with the dual variable uk plugged in. And then we have this augmentation term for the Lagrangian, and then we also have this proximal term. So obtaining the xk plus 1 update through this type of minimization corresponds to the proximal method of multipliers. But in this case, we do have the h term, but the h function, unlike the f function, the h function is not accessed directly, but rather we are accessing h through its gradient. So this is as if we are replacing the function h with its first-order Taylor expansion about the point xk, because this is equivalent to h of xk plus grad of h of xk, x minus xk. This term and this form only differs by constants that do not depend on x. So therefore, this is very much like the proximal method of multipliers, except that we replace the function h with its linearization about point xk. Hence the part function linearization. If total duality holds, if the function h is L smooth, and if alpha is between, the step size is between 0 and 2 over L, then the primal iterates converge and the dual iterates converge. Next, let's derive the algorithm PAPC, which also has the name PDFP2O. So we consider this primal problem. We minimize h of x plus g composed with ax. And here we assume the function h is differentiable and g is just a CCP function. This primal problem is generated by this Lagrangian. We had seen essentially the same Lagrangian before when we were deriving the algorithm PDHG, except in that case, here in the PDHG setting, there used to be the CCP function f. Now here we have the CCP function h, which in addition to being CCP, it is furthermore differentiable. We apply to derive the algorithms PAPC, PDFP2O, we apply the variable metric for backward splitting on the saddle subdifferential of L, and then we'll be using the Gaussian elimination technique. So this derivation actually is a result of the combination of two techniques. This derivation combines the Gaussian elimination technique with the variable metric technique. So first we characterize what the saddle subdifferential looks like. So the saddle subdifferential has this skew symmetric term, and then it has the gradient and the subdifferential operators, but we will put the subdifferential operator with respect to g star on this side, and we will refer to this operator as g. And then the gradient operator with respect to h, we put that here, and we'll refer to this operator as big H. In this setup, we will be using the metric matrix M of this form, which is block diagonal, although not being exactly diagonal. So here the off-diagonal blocks are 0. Here this part is diagonal, but this part is not diagonal. This metric matrix M is strictly positive definite under the condition that alpha beta times lambda max of A transpose A is less than 1. This condition is equivalent to saying that this lower right-hand block is positive definite. So now let's express the fixed point iteration with this variable metric for backward splitting operator. And when we do that, well, so this is the fixed point iteration maps xk comma uk to xk plus 1, uk plus 1. So first we apply m minus h to xk and uk, and this is what we get. So the h operator gives us this gradient step, and then the metric, the lower right-hand block of m gives us this form relating to uk. And then here, instead of applying the applying m inverse g directly, what we will instead do is we'll apply m plus g to xk plus 1, uk plus 1, and leave it on the left-hand side for the moment. So this diagonal component, this block diagonal component comes from the metric m, and these skew symmetric components come from the linear part of the operator g, and then the operator g has the subdifferential operator of g star, and that's what we have here. Okay, now if we solve for xk plus 1 and uk plus 1, we will get an algorithm given by this variable metric for backward splitting. So to do that, we want to have in this case, an upper triangular system. So to achieve an upper triangular system, we will left multiply the system with this invertible matrix. And when we carry that out, this matrix, when we left multiply with this one, becomes this upper triangular structure. This operator becomes this, and then this right-hand side vector becomes this thing. I'm skipping over the details of the calculations, so if you're curious, you may want to pause the video, carry out the calculations yourselves, verify that you indeed get the same result, and then continue with the video. In any case, now that we have a lower triangular structure in our system of inclusions, we are now able to solve for uk first, and then we can use that result to solve for xk plus 1. So when we carry that out, we compute uk plus 1 first, and that can be expressed in terms of this proximal operator. And then we can use that result, the uk plus 1 result, to compute xk plus 1. This method is referred to as the Proximal Alternating Predictor Corrector, PAPC method, or the Primal Dual Fixed Point Algorithm based on Proximity Operator, PDFB2O. If total duality holds, the function h is L smooth, alpha and beta are positive, this step size condition is met, and alpha is less than 2 over L, then the primal iterates converge and the dual iterates converge. Okay, now let's take a look at an example. This one is referred to as isotonic regression. So isotonic regression, as the name suggests, involves an isotonic constraint. An isotonic constraint requires all of its entries of the variable x to be non-decreasing. So this is the isotonic constraint. xi plus 1 has to be bigger than xi. And since we are performing regression, this type of problem arises from statistics, and in that context, the optimization variable is referred to as the regressor. If we perform isotonic regression with the Huber loss, so we solve this minimization problem with respect to the variable x, we have this isotonic constraint, and then we want to fit ax equals b, and then when there is a deviation from ax equals b, we use this particular Huber loss function element wise as the penalty. Okay, so this type of regression has certain applications, meaning in statistics, but for our purposes, we'll just take this problem as a given and try to see how we solve this. Well, what splitting method can we use? So here's a nice trick. What we will do is we will split the isotonic constraint into two separate proximable terms. So this is part of the isotonic constraint moved into part of the objective using the indicator function. But this is just part because we're not enforcing this constraint for all indices I, but rather the odd indices. So this is sum from I equals 1, 3, 5, 7, and so on and so forth. Then we have essentially the same type of function, but now the summation indices are different from 2, 4, up to n minus 2. Together, if we combine these summation indices, that constitutes the entire isotonic constraint. But the reason we split the isotonic constraints in this way is because this is proximable and this is proximable separately. Why is that so? Well, the coordinate x1 and x2 appears here for I equals 1, and the coordinate x3 and x4 appears here with I equals 3. So if you look at all the terms involved in this summation, the x coordinate only enters one of the terms here. Now here, in the second one, the coordinate x2 and x3 enters when I is equal to 4, and the coordinate x4 and x5 enters when I is equal to 4. So again, for all of the terms here, each x coordinate only enters at most one of the terms within this summation. Now, the coordinate, let's say x2, appears in one of the terms here and one of the terms here. So if you combine these two sums, because each coordinate of x appears within the sum more than once, in this case exactly twice, then the operation with respect to the proximal operator with respect to those coordinates become all coupled and becomes a mess to compute. But by splitting up the isotonic constraint into these two odd and even parts, we are able to evaluate the proximal operator with respect to these constraints in a very efficient and simple manner. So we split the isotonic constraint into two individually proximable parts, and then we have this third part with the Huber loss, and this part is a differentiable term. So we can use the dys operator to solve a splitting method to solve this optimization problem. Now here's another approach. What we can do is we can write the isotonic constraint in this form. So the objective function, the original objective function is left as is, but now the isotonic constraint can be written using this finite difference operator. So if you think about what the meaning of the isotonic constraint is, it means the individual coordinates are non-decreasing, they're increasing. And the continuous analog of that would be that the derivative is positive, or at least non-negative. So this corresponds to that. So we evaluate the finite differences of our vector x, and then we enforce that to be non-negative. Here, this is the explicit form of the finite difference operator. Once we've posed our optimization problem in this form, we can now use the Papc algorithm. Next, let's briefly step away from the lecture content to solve exercise 1.7 from the book. The problem statement of exercise 1.7 is as follows. We assume f is a CCP function that is furthermore proximable. We defined the function g, which takes in two inputs, x1 and x2, as f of x1 plus x2. Then the first part of the problem is to show that the proximal operator with respect to g can be evaluated using the proximal operator with respect to f. More specifically, the proximal operator with respect to g can be evaluated using this particular formula, which relies on the proximal operator with respect to 2 times f. Likewise, if we define the function h as h of x1 comma x2 to be f of x1 minus x2, so we have a similar definition, but now with the sign flipped, then we have a similar formula, again utilizing the proximal operator with respect to 2 times f, but due to the sign differences, there is some minor differences in the formula. This problem comes with a hint. The hint points out that the function g can be viewed as the composition of the function f with the n by 2n matrix with 2 identity block components. And the hint furthermore tells us to establish that y1 comma y2 is the output of the proximal operator with respect to g with inputs x1 and x2 if and only if there exists a subgradient of v evaluated at y1 and plus y2 such that these two identities hold. Let's solve the exercise. So for the first part, we again note that G is the composition of F with this n by 2n matrix with 2 identity blocks. And we also recognize that this particular regularity condition is satisfied because the range of this matrix is all of Rn, and the relative interior of the domain of F is non-empty because F is a CCP function. So this regularity condition is satisfied, and therefore the chain rule for subgradients holds. If we let y1 comma y2 be the output of the proximal operator with respect to g, evaluated at x1 comma x2, well, this is by definition defined as x1 comma x2 being within identity plus partial g evaluated at y1 comma y2. But partial g, due to the chain rule of subgradients, can be written as the transpose of this matrix, composed with f and y1 plus y2. This was the identity provided in the hint, and now it is established. By adding the two identities of the hint, so we have x1 is equal to y1 plus v, and x2 is equal to y2 plus v, where v is a member of partial f evaluated at y1 and y1 plus y2. We add the 2 and we get x1 plus x2 is y1 plus y2 plus 2 times v. Well, 2 times v is is a member of the subdifferential of 2 times f evaluated at y1 plus y2, and this one goes over here. So if we examine the left-hand side and the right-hand side, this is an inclusion defining an evaluation of the proximal operator. In particular, this inclusion tells us that y1 plus y2 is the output of the prox of 2 times f evaluated at y1 plus y2. And then plugging this evaluation into here, and solving for v, we get that v is 1/2, and then with this formula. So plugging this v into here and then reorganizing gives us the desired first result. For the second part, we had the function h defined as the composition of f with this n by 2n block matrix with the identity and the negative identity block. The result follows by essentially the same reasoning. So we define y1 comma y2 as the output of the proximal operator with respect to h evaluated at x1 comma x2. And this holds if and only if we have this equality where v is a member of partial f evaluated at y1 minus y2. And following the same type of reasoning, we get this formula and then we get the expression for v. and then plugging this formula for v into here and reorganizing, that gives us the second desired result. Next, let's take a look at some Python code implementing the isotonic regression example. So again, you can download this code, you can play around with it, you can execute it yourself. So I'll keep the discussion of the implementation very brief. Just to be clear, what you're seeing here is a Jupyter notebook. So if you want to execute what you see here, you need to download the Jupyter Notebook software in addition to installing Python. So in the first step of this program, we make some necessary imports. In particular, we import this CVX-Pi library, which is a solver for convex optimization problems. And we do so because this way we can solve the problem once using CVX-Pi, and then we can compare the result with the use of DYS and PAPC. So we import the necessary libraries, and then we generate our random data. So we generate our data matrix A, we generate our true unknown solution X, and then we compute A times X. By the way, this @ symbol, this is the matrix vector product in Python. And then we add a little bit of noise, and that's our measurement in B. We then define our Huber loss function, and we also define a function that evaluates the gradient of this said Huber loss function. Okay, so the first step is we will use the solver CVX-Pi to solve this isotonic regression problem. So we specify the objective to be this Huber loss, which is provided. The Huber loss is provided as a built-in for the CVX-Pi library. And we specify our isotonic constraints in this way. So this is a pretty cute way of specifying constraints in CVX-Pi. But in any case, so we solve it using the solver, and the solution looks like this. So one could spend some time trying to interpret the solution, trying to get an understanding of the meaning of the solution in some statistical sense. We won't do that. We'll just move on and see how the problem gets solved using DYS. So to use a DYS, well, we performed the decomposition into the odd and even constraint terms as described in the slides, and then we apply the proximal formula of exercise 1.7. Well, if you actually carry that out in full and then write out the code for performing the projection onto the even sum term and the odd sum terms, this is what you get. So if you're interested, you can take a look at this code, but this is the proximal operators with respect to the two. So this is the proximal operator with respect to the two sums. Okay, so now that we have these projection operators, well, now the application of DYS is straightforward. So this is it. So this is the three-line description of the DYS algorithm, where we apply the proximal operator, and the gradient operator. So we print out the result. The optimal value for CVX-Pi is this. The optimal value for DYS is this. It's basically the same thing, and if you compare the solutions, they also come out to be essentially the same thing as well. Okay, so next we had the PAPC iteration. So for that, we define this matrix D. So this was the finite difference matrix D, and here I'm using here I'm using some Pythonic notation. In any case, you can print out this matrix D to verify that this indeed is the same matrix D that you see in the slide. And then to perform the PAPC iteration, we define some initial values for X and U. We just set that to be equal to 0. We need to choose the alpha and beta step size parameters. We choose that to be just whatever. And then we execute the algorithm, and this is the two-line description of the PAPC algorithm. And when we execute this, well, the result turns out to be, we get exactly the same thing. So we have the same optimal value as CVX-Pi, and when we print out the solution, we get the same solution as well. So now that we have two methods that we can use PACP and we have DYS, and also we have another thing that we can use, right? We can also use the CVX-Pi solver. So since we have multiple choices for solving this given problem, one could try to compare the efficiency of these algorithms by measuring the rate of convergence, how fast the algorithms converge to the solution. But for the sake of conciseness, we won't make that comparison. We'll be content with observing that both approaches, both DYS and PAPC, led to an algorithm that converges to the solution.